Supernovae, which are catastrophic star deaths, produce black holes. So what exactly is a white hole in the universe? We will speak about white holes today. Let's discuss black holes first before moving on to white holes. What exactly is this thing you have with holes, before we discuss black holes? In the universe, black holes are regions where matter and energy are packed so tightly together that they can no longer escape at the speed of light. Even though we've made at least 1 million films on them, if you're still interested in learning more, start with our black hole playlist. Black holes are actual things in our universe, but defining them fully involves a lot of complicated math. They were really found throughout the past few decades, as predicted by Einstein's theory of relativity. When stars that are significantly more massive than the Sun explode violently in a supernova, black holes are produced. What is a white hole, then? When astrophysicists analytically examine the region surrounding black holes while assuming there is no mass within the event horizon, they produce white holes. What transpires in the case of a black hole singularity devoid of mass? White holes are wholly abstract mathematical ideas. According to those who work in black hole mathematics, it is really more simpler to ignore the singularity's mass. They don't genuinely exist as things. It's not as if astronomers discovered a strange radiation burst and then created fictitious white hole models to explain it. Dr. Brian Koberlein says you eventually run out of cupcakes if you start with 5 and start sharing them. You are then unable to give anything away. You can't go past 0 in this scenario. Sure, you can pass out pieces of paper with the words "I owe you 1 cupcake" inscribed on them, but it would be absurd to suggest that negative cupcakes are real and that you can give them to people. White holes would act like reverse black holes, as predicted by mathematics, if they did exist, which they most likely do not. A white hole would eject matter into space like some sort of white chocolate fountain rather than drawing matter inward. These white holes and their chocolate are so giving. The fact that white holes can only exist in theory as long as there isn't even a single particle of matter inside the event horizon is another conclusion of white hole math. A single hydrogen atom drifting into the area would cause the entire structure to disintegrate. White holes would have collapsed long ago even if they had been generated at the beginning of the cosmos because our universe is already brimming with stray matter. However, some physicists believe white holes may be more real than previously thought. Theoretical physicists Hal Haggard and Carlo Rovelli of the French University Aix-Marseille are utilizing loop quantum gravity to explain what occurs within black holes. A black hole singularity would theoretically shrink to its physics-predicted lowest size. It would then bounce back as a white hole. However, even the lowest mass ones would take billions of years to finally pop because of the extreme time dilation effect that surrounds a black hole. The disintegration and explosion of any small black holes that may have been generated after the Big Bang could happen at any moment. Except that, in Stephen Hawking's opinion, they already would have vanished. Another intriguing hypothesis put out by physicists is that the Big Bang may have been caused by a white hole, as this is another instance in which a massive amount of matter and energy spontaneously formed. Most likely, white holes are just complicated math. White holes are probably just made up, as sophisticated math rarely holds up to encounter with reality. There are 2 distinct outer regions of the maximally extended spacetime, which are frequently referred to as 2 different universes, just as there are 2 distinct interior regions. The second universe enables us to extrapolate certain potential particle trajectories in the 2 interior regions. This means that particles from the interior white hole region can also escape into either universe, just as particles from the interior black hole region can contain a mixture of particles that entered from either universe, and as a result, an observer entering from one universe may be able to see light entering from the other. It is possible to create coordinate systems in this spacetime such that, if you choose a hypersurface of constant time, a collection of points with the same time coordinate, giving a space-like surface, and draw an embedding diagram depicting the curvature of space at that time, the embedding diagram will resemble a tube connecting the two exterior regions, known as an Einstein-Rosen tube. The Einstein-Rosen bridge can connect two black hole event horizons in each universe, with points in the interior of the bridge being part of the black hole area of the spacetime, or two white hole event horizons in each universe, depending on where the space-like hypersurface is placed, with points in the interior of the bridge being part of the white hole region. However, as it is impossible to enter a white hole event horizon from the outside, and since anyone approaching a black hole event horizon from either universe will inevitably collide with the black hole singularity, it is impossible to use the bridge to travel between the two universes. Note that a more realistic black hole that originates at a specific period from a collapsing star would require a different metric. The maximally extended Schwarzschild metric represents an idealized black hole/white hole that lives eternally from the perspective of external observers. The portion of the diagram that corresponds to the white hole interior region is removed when the infalling stellar matter is added to a schematic of a black hole's history. General relativity must, however, permit the time reverse of this kind of actual black hole that develops from collapsing matter, since its equations are time reversible and exhibit time reversal symmetry. A white hole in the universe's past that has been emitting matter until it finally explodes and vanishes would be the time-reversed example. Although such objects are theoretically possible, physicists do not treat them as seriously as black holes because there would be no processes that would naturally lead to their production. Instead, they could exist only if they were included in the Big Bang's initial conditions. Furthermore, it is predicted that such a white hole would be extremely unstable in the sense that it would be prevented from exploding as seen by distant observers if even a tiny amount of matter fell toward its horizon from the outside, with the matter emitted from the singularity never being able to escape the white hole's gravitational radius. A singular black hole is created by the gravitational collapse of a sufficiently compact mass, according to general relativity. The repulsive spin-spin interaction, which is substantial in fermionic matter at extremely high densities, is produced by the minimum coupling between torsion and Dirac spinors in the Einstein-Cartan theory, though a gravitational singularity is avoided by such an interaction. Instead, the material that is collapsing on the other side of the event horizon achieves a massive but finite density and bounces back, forming a typical Einstein-Rosen bridge. The cosmos on the other side of the bridge develops into a young child. The parent universe appears as the solitary white hole to observers in the baby universe. In light of this, the observable universe can be described as the Einstein-Rosen interior of a black hole, one of many that may exist inside a bigger universe. The observable universe had a finite, minimum scale factor at the time of the Big Bang, which was a non-singular Big Bang. According to a 2012 research, the Big Bang is actually a white hole. It also implies that the formation of a white hole, often known as a small bang, occurs spontaneously since all the matter is ejected in a single pulse. White holes cannot therefore be continually monitored like black holes. Instead, their effects can only be seen in the immediate vicinity of the event. Even finding a new class of white hole-containing gamma-ray bursts was suggested in the paper. In 2014, Madriz Aguilar, Moreno, and Bellini investigated the hypothesis that the Big Bang was caused by an explosion of a supermassive white hole in a five-dimensional vacuum. was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.